So now we've got a person standing on an elevator. So, not a scale, in an elevator I should say. So their mass is 98.1 kilograms. So before it moves, the only force is mg and a normal force. So the normal force is from the scale. So F net is equal to normal minus mg, which equals 0, as the acceleration is 0, so we're not moving yet. So then n equals mg. So the scale reads n over g, which equals m. So that's what the scale reads, is its normal force over g, or the force it needs to apply. So when now the elevator is accelerating upward, then we've still got an mg, we still got our normal, and we've got an acceleration of 1.47 meters per second squared upward. N minus mg is equal to ma. So n is equal to ma plus mg, which is equal to our mass, 98.1 meters per, no wait, yeah, 98.1 is right, but it should be kilograms. Our acceleration is 1.47 meters per second squared, and our g is 9.8 meters per second squared. And so this comes out to be 1105.587 newtons. And so the scale will read so it still will read n over g, so 1105.587 newtons over 9.8 meters per second squared, which is 112.815 kilograms. And so just as a check here, right? So when an elevator is accelerating upward, that's either at the beginning of an elevator journey upwards or when it's coming to a stop as it's traveling down. And so you'd always feel heavier when that happens. And so a scale would read heavier. So that makes sense. If we check the solution here, so they calculated a net acceleration and got an apparent weight that was actually less, but that doesn't make sense from what we were just saying, and so that's just incorrect. And the best way to do it is just to break the components down as opposed to trying to find a net acceleration. I don't actually know how to look at force components and how scale reads mass. So I'm just going to do that.